Hi everyone, I am Niyazi Şenol from Ulum University. I'm PhD student and also engineer in Turkish aerospace in Ankara, Turkey. Hasan Akai is from Ulum University is my PhD advisor, and Dr. Şahin Yiğit is our manager from aerospace, Turkish aerospace. And my presentation is about a surrogate model-based shape optimization framework for compressible flows. This is my agenda. I will give some brief introduction and then mathematical background of optimization, and we'll describe the test case, we'll discuss the results, give conclusion, and then references. In this study, a shape optimization framework is designed and developed to be used for compressible flows, especially for aerospace applications. Within this framework, all of the elements, the open source libraries, in order to compare different surrogate model base, kriging, gradient enhanced kriging, gradient enhanced kriging with partial least square methods are investigated. And also to be able to investigate different flight conditions, single point and multi-point optimization are studied. In the literature, there are lots of shape optimization. In the surrogate-based optimization have been preferred due to their main advantage. Like they perform a global search, but in adjoint methods, like they are not getting stuck locally. Also, these methods can handle problems with unknown or discontinuous gradients, making it suitable for a wide range of applications. And also, GEC and GEC PLS methods are used. The power of these methods is increased by using the adjoint method in the framework, since it provides gradients for GEC and GEC PLS. So this is our framework flowchart. We are using efficient global optimization EGO cycle in our flowchart. In the previous studies, we used this flowchart only with the kriging method in step 4. Now we are introducing GEC and GEC PLS in the flowchart. You see, we have a baseline shape in the first step. So we are doing initial sampling, design of experiment parts. We are using Latin hypercube sampling in this step. And in the step 3, we are mesh deformation. So here for shape classification, we are using the freeform deformation, FFD. So in the step 4, we solve the domain flow solver with the SU2 code, SU2 CFD code. So in the step here, if you are using the kriging, these are we are constructing surrogate model. But if you are using the GEC and GEC PLS, you need the gradient information. So you have additional step in adjoint solver. So SU2 has also capable to get a adjoint here. So after construct the surrogate model, in EGO cycle, we are in field sample criteria. We are using expected improvement here. So it gets a point, it's a new sample. So mesh deformation, flow solver again, and with GEC PLS adjoint solver or without, in kriging without the convergent. If your convergent criteria satisfies, yes, this is the optimal shape. If no, its cycle goes around. So in the gradient enhanced kriging, our aim is to improve the kriging method using the gradient information at the sample points. Generally, they are giving the more accurate results. So dataset S and Y used when constructing kriging models, and you see in equation 1. And the GEC model is defined in equation 2. you see additionally we are adding the gradient. You see in the y vector we have n plus variable here. So, but GEC also some disadvantage because you are increasing the size of correlation matrix and the number of hypermeters to be estimated. Bullell proposed a new method, GEC-PLS, and demonstrated its reliability. When you're constructing a model in the GEC method, your correlation matrix size is m plus d plus 1 square. N is the number of sampling points, and D is the number of the points around each sampling point. In GEC-PLS, the advantage is that instead of D, you are using M when constructed your correlation matrix, and it improves the condition number of correlation matrix and enables the construction more accurate models. So in our framework, we are also handle the multi-objective optimization. The main idea here is find the global minimum or maximum, it depends on your problem, for each objective simultaneously. You see an example of Pareto front. Pareto front is, they give the non-dominated solutions, and above the Pareto front is dominated solutions. So in our framework for multi-objective optimization, we also use the surrogate model toolbox, SMT, and Smooth and PyMu codes for multi-objective optimization. So I will describe my test cases. We will use RAE 2822 airfoil. This is the proposed by AIAA Aerodynamic Design Optimization Discussion Group for researchers in the fields of CFD and design optimization. The condition is that viscous and transonic follows with the different flight conditions with some design constraints. In the first step, we will use single point, and then we will move multi-point optimizations. Here, what's multi-point optimizations? If you have more than one flight conditions, you have to use the multi-point optimizations. We mentioned about the Kriging, GEC, and GEC-PLS method. For the comparison purposes, we also add the adjoint method here. And also, the first three methods, we got the solutions with proposed framework. For the adjoint methods, the results obtained with this achieved by using SU2 code. This is our test case definition. The flight condition is Reynolds number 6.5 million. The Mach number for a single point, 0.734. Initial angle of attack is 0 degree. We have a constraint, lift constraint, aerodynamic constraint, 0.824. And the third one is the geometrical constraint. The optimum airfoil area must be greater than or equal to the initial airfoil area. And turbulence model Spalatan-Maras. For this comparison, the recent work by Koretikere and Leifson. This is the single and multi-point drag optimization study. We refer this one. So in the figure 2, you can see our mesh. The first one is the far field mesh, and the second one is near the surface. And the figure 3, you can see the FFD box. We have 8 FFD box and 18 design variables. Design variables points, they only available only in the y direction, they move. Single point optimization definition is your target is minimize the drag CD, and subject to the CL is 0.824, and A area is equal or bigger than the baseline area. For multi-point optimization, your total CD has to be minimum, and also they are subject, they're similar for all the flight conditions. For the multi-point conditions, 1, 2, 3, we have 3 points. The weights 0.25 for point 1, and point 2 0.5, and for 3 0.25. Their Mach number is represented here, and CL and AI conditions constraint represent here. Before the results, we work on the speed up study. In 10 minutes, in elapsed time, we run different various number of processors, serial 2, 4, 8, 16, and 82. We tried the processors number. So in the 4 serial, number of iteration is 5 for 2, 9, 15, 25, 30, and 28, 26. For the speed ups, we select the 16 number of processors because the speed up is high here. So after that, are all study with the 16 processors. For single point optimization, these are the results table. So in the first column, 3 column is referred are references. Their base, and they use CEGO and CEGO neural network. So the improvement is like 40, 48, 43, and 42 is very close. In our base, is similar, very similar. But in Kriging and GEC PLS, our improvement is good and above their improvement. And adjoint is not good. The improvement is nearly half of these ones. And angle of attack is changed due to the apply the CL conditions. And these are the time in minutes. Compared to the result, it can be easily observed that there are more efficient methods in CD values. And adjoint methods, it seems to lag behind the methods and time and efficiency. In figure 4, you can see the CPU distribution. In the CPU distribution, in the base airfoils, they have a shock near 0.5 x over C. And the other methods improve the airfoil. You can see in the airfoil shape. So this is the objective function CD versus design iterations. And the first 25 is design of experiment. And then we are giving 50 design iteration. You see their ego and ego neural network. Ego is a good agreement, but our Kriging and GEC PLS, GEC PLS is a good agreement and stable, but the GEC is not stable. An adjoint method, you see, is very fast, but it's stuck in locally, like 150 degree CD. By the way, CD is in the drag count. This is the multi-point optimization results. So we have base CGO and CGO-NN neural network, and we have base kriging, GEC-PLS, and adjoint. In here, our GEC improvement is not good. I think it's due to high number of design flight conditions. But GEC-PLS is higher than the other methods. Adjoint method is also behind these methods, all methods. Okay. Contrary to expectation, under GEC underperforms methods kriging and GEC-PLS. Maybe too many gradients have caused GEC to perform poorly. So this is the airfoil shape, and the shape is 1. And we have CPU for 0.1 and 0.2 and 0.3. So this is the comparison of models. In here, GEC-PLS is very stable rather than the other methods. We designed a optimization framework that for single and multi-point optimization. In terms of computational time, both methods GEC and GEC-PLS seem to be higher than the kriging. This is because they are using the gradient calculations. In the multi-point optimization, GEC method falls behind the other methods, but GEC-PLS method is both stable and has higher improvement. As a future work, we will move on to three-dimensional problems. And these are my references. Thank you.